Today we are going to show you some of the experiments Galileo Galilei carried out to study the law of falling bodies.
The answer we developed for Aristotle believed that here an object was falling down.
If we drop a hammer and a feather, Aristotle's ideas seems to make sense. Now let's see the fall once in slow motion.
The legend says that Galileo dropped some different weight cannonballs from the Leaning Tower of Pisa.
Well, we don't have here the Tower of Pisa and the cannonballs, but we have a basketball and a tennis ball.
So first of all, let's weigh the two objects.
$613 grams. $15.8 grams. As you can see, the bodies have a different weight.
Let's drop the two balls, with the heavier ball be the first to hit the ground, as Aristotle had thought, or will the two balls arrive at the same time, as Galileo claimed. Okay, let's try, shall we?
And the winner is Galileo. He was right.
Let's try it again with other objects from different weights.
The objects always reach the ground at the same time.
Why then the feather or the piece of paper float down more slowly?
The answer is they are slowed down by the air presence.
Indeed, if no air was present, as the feather and the piece of paper would fall just like the hammer, and demonstrated by the astronauts during the Apollo 15 mission of the Moon in 1931.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. I have a good picture there. I've got.
Beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago, who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
We can prove that Galileo was right by using some pendles consisting of a thin cord with different masses attached.
We see that all pendulums swing back and forth, taking the same period of time to make one swing. But bodies fall too rapidly to study their motion.
Galileo understood that he could slow the falling motion down by making them roll along an inclinated plane. We have built ourselves an inclined plane similar to the one used by Galileo in order to find the relationship between space and time.
Along the inclinated plane, we'll put some little text and some bells, which will help us to measure the time that a roller body takes to travel the distance between the start and the finish.
Now let's measure the distance between the starting point and the distance of the vessel. 10, 30, 50, and 70.
The first unit of distance is 10 centimeters. The second is 3 times as long, 30 centimeters, so the total distance will be 40 centimeters, 4 times as long as the initial measure.
The third unit of distance is 50 centimeters, 5 times as long as the initial unit, and so the total distance will be 9 times as long as the first measure. The final unit is 70 centimeters, 7 times as long as the first one, resulting in a total distance of 16 times as long as the initial one.
Now we measure the times and we will clock how long it takes to travel from the starting point and each station with the best, and by difference how long it takes to go from one ball to the other. Three, 2, 1, go! Go!
Now we change the plane slowly.
Sì, gravi Palli.
3, 2, 1, go! Go!
We record the data in an Excel table.
The first inclination,
1.09,
2.09,
3.12,
4.18. The second inclination,
0.92,
1.62,
2.4,
3.19.
We see that the time used to travel each unit from one level to the other is always the same, whereas the time in total increases and gradually becomes twice, 3 times, 4 times as much.
We've come to Galileo's conclusion that the distance a free-falling body travels is directly proportional to the square of the time.
We have finally discovered the relationship between space and time, and where A stands for acceleration of a body.
This experience allowed Newton to formulate the fundamental laws of body dynamics a few years later.
Still today, it is possible to reach the moon, to send space probes to explore the solar system, and to exactly predict a solar eclipse. We should be thankful to the laws formulated by Galileo Galilei and Newton then more 300 years ago.